Ahoy, 216ers. This is Professor Kaufman, and what follows will be an introduction to Project 4, which will have you constructing a small command line shell. Just a few words of preamble here. The name for the shell is Shellac, and someone asked me in lecture the other day, what is shellac? It's a component in varnish, which is sort of a paint or covering substance that you would apply to wood to protect it. It's a thin coating, and I think that's apropos because most command line shells are a sort of thin coating over something more substantial underneath. Command line shells, you use them, for instance, the little command line shell over here where I can ls things and so forth. This is a sort of thin shell or coating over the underlying operating system kernel that provides the facilities the system calls to do things like do directory listings or create files and run programs and so forth. So the emphasis of Shellac is just to get you to A, write a little C program that does some more interactivity with the user, and B, then exercise some of your newfound knowledge about command lines or about system calls to fork off child processes to run jobs like ls and so forth, as well as do a little bit of command line redirect IO redirection. So the shell itself, the building of it is divided into three problems and they stack, so it's best to go in order here. The first problem will have you building the basic sort of outline of the interactive loop and not dabbling too much in any of the system calls. It's relatively short and a lot of it can be accomplished by drawing from past projects and or labs that we've done. The second problem is where we get into the nitty-gritty parts of this, where you'll build some underlying C functionality, work with some data structures that encapsulate to some extent a job, like a child process that's going to do something on behalf of the shell, and then elicit just a little bit of control. But by the end of that, you'll be able to do things like fire up Shellac and do some LSing and so forth. And then the last problem adds some standard C features, or shell features, which are to redirect I.O. from a job into some file, or redirect I.O. from a file into the job as it would want to read standard input. And as well allow for the creation of background jobs, which is something that is useful in most shells, but beginning practitioners don't necessarily know about it. So we'll step through some aspects of each of these, but I think the best best way to sort of get acquainted with what's happening with Shellac is to just look at what the completed implementation looks like. Scattered throughout the project specification is our sample sessions of like, oh, at this stage you should be able to do the following kinds of things. And it's useful to sort of look at those and sort of take in, like if I started Shellac, then I can press enter or about tokens or I get a help and so forth. But I think just sort of demonstrating the end goal of what it looks like is useful. So for that, I'll start this out by just looking at the completed solution that I have for this. I think I've built it, yep, already. So if I start Shellac in here, then I get a little prompt over here. And like some other command line shells, they'll just have like I can ask for help and so forth. And it's a limited number of commands that you'll essentially lay out the cases for this in the interactive loop for this in problem 1 to say, oh, I'll recognize built-in commands like help and exit and jobs and so forth, and pause and wait and tokens. But the main essence of this is to anything else that doesn't match any of these, you find the program named command and run it. So this could be like ls or gcc or something like that. So the boring ones like with help and so forth or jobs, they print some things and we'll sort of develop that further. But the interesting one that'll be in reach after problem 2 is completed is, oh, I can ls in here. And what you'd see in this case is some preamble here to say Shellac is starting some job, but then the child program, ls, is launched as a child process, and it's exec, so it becomes ls, and it actually spits out things to the screen over here. And Shellac detects that it's finished and then prints out a little postamble down here to say like, oh, this was the process ID number and it exited successfully. I can do this with whatever else. So GCC, and I can ask maybe for a version for GCC, and it shows over here. Again, starting it up, this is the child process printing out stuff over here, and then eventually completing. I'm trying to think of some other ones. A common sort of testing example is the seek program, which prints out sequences of numbers. So seek 10 prints out 1 to 10, or I could do seek like, let's see, 5 to 25 by 3's 25 here. And so I get stuff like that. One minor annoyance that you'll probably find is that most standard shells and terminal emulators, they actually respond to arrow keys and backspace and stuff like that. Shellac isn't that sophisticated, so if I make a mistake, like seek 510, and I wanted to go back, if I press the left arrow, then you'll see this garbage come on, and that's just because we're not implementing like, when you press left arrow to try to go backwards, it actually sends a certain character to the program that's interpreting that. And the behavior has to be interpreted correctly. It's like, this isn't something you put on the screen. This is something that you want to do in terms of manipulating an internal state of the program. Shellac doesn't have that, so you just have to sort of work with it in its primitive state. So no command history either, with like up and so forth. But at least backspace works, so you got that going for you. Okay, so other things then, the end goal here is to complete problem 3, so that allows redirection as well. And so you can do things like, here's sequence 1 to 100, but I will redirect that using the standard sort of redirect character, this little greater than sign, into some text file like 100.txt. You'll see in this case, Shellac detects starting this up, and now it's completed. There's no output because the output for the child program has been redirected into this file over here, 100.txt. I can as well then look at what's in there using the head command. It prints out the first 10 lines by default of text files. So here's head.txt. Don't even need to go to another shell because I got a reasonable one here with Shellac. I can also look at the tail of that and see. Sorry, I spelled it wrong. Tail 100.txt rather, and see the end of the file over here. You can see, so one other feature here, my original tail up here that I spelled this wrong, it printed out an error message and gave a non-zero return code to indicate I didn't actually complete normally here I completed normally, but I didn't do what you told me to because I couldn't find the file. And so an exit code of 1 is common for child processes that don't complete normally. And so this is something that Shellac's going to pick up and detect on. So try not to always print out exit 0 over here when you get to that stage. So that's output redirection. That if you look back up here, it created this output file with 100.txt. I could also do something like do input redirection. So here's a word count. It counts how many words, characters, lines are in a file, and normally it would read from standard inputs or accept a file, but I can pipe in, here's 100.txt, like how much stuff is in there. And you see, like I don't need to type anything or give anything else. It'll read stuff out directly from there and say, there are 100 lines, 100 words, and 292 characters in there. Some handy utilities to know about there. The final version of this, the thing is to support background jobs, which is a semi-advanced feature. And if you haven't seen this in standard shells before, the type of behavior we're trying to do in Shellac apes what you'd get in like Bash or about the sort of other standard shells there. The idea is as follows. That you might have a long running job that takes 10 seconds to run. I can simulate that using some of the tools that are provided in the code pack. So there's a program test data / sleep print.shell, if I remember right. And this will take a number, but to say how long to wait and then what to print afterwards. So I'll print out I am awake after that. So wait 3 seconds and then print something out. If I punch enter now, the parent process Shellac is going to block because its default behavior is to wait until this one's done. And when it actually is done, that 3 second time, it'll print out and then finish, and this thing will exit then. This is slightly annoying, particularly if you have something like, here's a test data sleep print.shell, and there's going to be a 20-second delay on this. I am awake after 20 seconds, something like that. So I'll launch this in the background, and that's usually designated by the ampersand sign in standard shells. This will trigger Shellac as it analyzes this line to say, oh, you want this in the background? That's cool. As I punch enter, look at a printout that has started, but I get my shell prompt back right away. You can check what's running in the background, and there's this sleep print thing with here. If I'm fast enough, I might be able to get another one up here. 10 awake now, and I'll plop that in the background too. Oh, I didn't spell it right. Sleep print. Okay, so we'll get that and just get to that in just a second. Here's the output from the original job, the sleep 20 that I had before, and you can see it's sort of interspersed with other stuff on the command line here, and that's in part as well. Like this gets a little bit muddled because I'm launching things in the background, and so it's unpredictable when the output's actually going to occur. It occurred for this failed job, like right here when I was waiting for another command, and occurred here for the earlier job as it's completed here. So oftentimes you just punch enter a couple times to sort of get this thing up, and you'll see the background jobs there that launched. The first one, the earliest one that was running, that was the sleep print 20. It completed successfully, and as well the sleep pring where I had this misspelling. This was launched in the background, but now we're getting reporting on it that it failed because there was no program found named this. It was a misspelling on that. Now to do this right, I'm probably going to need a little bit of assistance, so I'm going to cheat just a little bit here. I'm going to bop over to Emacs because it has a slightly different take on providing shells where I can actually use command history and so forth, and one of the many advantages it provides. So let me find this. It'll be 216 projects P4 and the solution for it. Yep. So I'm going to start a shell in here, and if now I start Shellac, I can, let's see, we'll do the test data / sleep print. I see I did it again. It's 20 and awake 1, and we'll launch that in the background, and thankfully in Emacs I can just start up a bunch of these here, and maybe I'll make this a shorter one, 10 here. So if I ask now jobs, like there are actually 4 running in the background, and if I wait for a little while, we're probably going to see some output like pop out here, so I'll just be patient and take a sip. Yeah, there's awake number 3 finished first. Don't know why awake 3 finished first. There's awake 1 and awake 2, etc. Let's see, did I? Oh, yeah, sorry. The 10-second one I finished first because I forgot to do that. So you can see the output here, it gets sort of interspersed that the cursor was waiting here, but then the output sort of printed from that spot and carried a line down, so I don't have my prompt back. As I press enter now, will be a check to like, oh, Shellac actually figured it out. All those are done in that respect. So this gives some insight into the general behavior of every time there's a command loop where you accept input for something. If that input runs a job, it'll be weighted, but then any background jobs are checked to see if they're done as well. And that's functionality that you'll see reflected in some of the C code that you'll eventually write. Is that I have an array of jobs that are running in the background, and each iteration of read a command like help at the end of executing that, or waiting on whatever child job was run in the foreground here, check on all this array of background jobs to see if it's there. And there's some specific information that we'll survey just briefly about how to go about doing that. Okay, so then I'm going to exit out of this for the moment, and I think we're in position now to begin talking through some of the spec items here. The first problem up here just has you building an interactive loop, not launching any child commands, but setting up the framework so that, oh, here's a spot where I will handle sort of the inputs, here's a spot where I'll recognize some of the built-in commands, and so forth. There's, some to do in this respect, but there's scaffolding to help provide for what was happening. For instance, provide you the print help function so that you don't have to worry about getting that character-wise right, as well as descriptions of what each of these built-in commands are supposed to do. In the case of like exit, obviously break out of the interactive loop and quit out of the program. Jobs list for now, print out 0 jobs, but we'll have to modify that later, as well as a few other things over here. The interesting one is tokens, as this has to do somewhat with how you'll read inputs in the program. And there's some description over here that you'll want to make use of a function called fgets. This one reads an entire input line. And the previous interactive loops that we've developed have usually used fscanf to like read one part and then realize, oh, I need to read more, so I'll read another thing, or oh, it's good enough to sort of see this. I can print out the tree or print out the list or something like that. This is inappropriate for the program that we're working on right now because it's hard to sort of determine how many things should I read if I'm launching GCC and it has some options like -G and -O and with a program name, and then several source files that are to be compiled. You don't know necessarily how many parts they're going to be. So the only sort of way to handle this is read an entire line up to a new line there. And then make use of something to sort of split that entire string up into chunks there. So there's some description here on the input lines and tokenization, but I worked with one student who made the mistake of, oh, I'll fscan stuff and also fget some stuff. Favor just fgets, and this is an indication of what you might want to do here. The 64 I chose is rather small, actually, so you'd want to maybe use something bigger than that. We'll look at the header file to say, oh, lines can be up to yay long, so some constants there for that kind of stuff. The next step on this is then to try to take and split up the items that are in an input line. So this will get you an entire input line like gcc-o prog source. I'm redirecting that into output.txt or something like that. What I really want is some way to say the 0th thing on this was gcc, the thing that followed that is -o, the thing that followed that is myprog, etc. Then this is a bit of a tricky kind of function to write, so I've provided it for you in a utility file called tokenized strings, and this is an example of how to use that function. You call it on an input, but then I have to provide where do you want me to put the tokens, or direct you to tokens, and where do you want me to store how many tokens there were in that respect. So making use of this has several interesting effects. First, after calling it, you'll be able to look in tokens, which is uninitialized right now, but will be initialized by tokenized strings. And you'll see, oh, there's the 0th thing points to a string, that's GCC. The 1th thing will be this -O, the 2th thing will be myprog, etc. And so your case analysis to determine later on, like, oh, is it pause, is it jobs, etc., is you read the input line, you tokenize it, and you say the 0th thing, is that exit, is that pause, is that wait, or if none of those things, then I'm supposed to run this as an overall command. The technique that's used often for this kind of processing in C is to use the dreaded stirtalk function. You can look that up if you want. It's what I used here, but it has a weird sort of set of semantics that are totally appropriate for C, but really fly in the face of what you do in any other program environment. And it will actually take this input string and modify it so that, oh, if there's a space here, I'm going to put a null terminator. And you can give a pointer to GCC here so that you can see, oh, this first string is actually part of the original string, and the second string is part of the original string. And so these aren't separate and distinct, and that'll have some consequences for memory allocation later on. But for case analysis and printing out tokens and so forth, that's not too bad. So that means as you'd implement this tokens subcommand here, or this built-in command, it's really just, oh, you've already parsed out the line, just print out output that sort of looks exactly like this thing over here. Just print it so that we can see your program's parsing input appropriately. Let's see, other things for the first part of this, exit and input, and oh yeah, there's command line echoing. That needs to be supported to be compatible with tests, and I think that's it for this, along with a demonstration of what this would look like afterwards. So I think the best way to sort of get started on this then is I'm going to take a moment now, probably the next 5 minutes, to lay out the groundwork for how to get started on this to solve problem 1. And then we'll round back over to discuss aspects of the remainder of problems 2 and problems 3 to give you a heads up what's happening there. But as usual, I want to download the code pack, so I'm going to grab the link address here. Goes over to Emacs, and rather than do this here, I think I'll go into a temporary directory Let me call this P4. And, oh, there's already a P4. Okay, 216 P. Well, sure. It's embarrassing. There we go. Okay, that's good enough. And I'm going to change my shell in here and do a wget with that link so I can download it directly. It'll be in here. And then I'll unzip that p4 code.zip, which will create my directory here, and I'll change into that p4 code in here. And over here, I'll see I've got a header file, some utilities, and then basically a bunch of testing. So there are some required files that you'll need to create either now or later. And those are listed in the project overview. The basic synopsis is we'll provide the header file and this little set of utility files, but you are ultimately responsible for creating the main, the job, and the control. Main is the interactive loop, the focus of problem 1. But then Shellac job and Shellac control, they deal with a job T struct that's described in the header. We'll look at that in a second. And the control deals with manipulating a Shellac T struct that's essentially just a glorified array of jobs as you manipulate. And those are the subject of development for problems 2 and 3. So let's get this Shellac main in order. As I've done previously, and hopefully you've done previously, it's not a bad idea to lift code from some previous spot that is related to the task at hand. And since my memory is pretty good of this stuff, in Project 2, you developed a little tree application that had a tree main in it and manipulated the tree using some interactive commands. That would be one easy prospect to get the basics of the interactive loop, and B, this command line echoing stuff in some form that's supposed to be there. The other spot that you can grab that from is one of the past labs or discussions here. So let's pull that up. I think let's, yep. And if memory serves right, this was discussion 2, which had you working on sort of building stuff. There was this list main here that we'll grab out. So let me copy that one. Hopefully you have your own copy around someplace and can do your own thing. I am going to change up a directory and grab this thing offline and unzip let's see, discussion 02's code. That'll be me over here to see discussion 2. This is mainly what I want, is the list main here. So within this, I'm going to copy my discussion 02 code, that list main, let's see, over into P4's code, and I'll call it Shellac main here. Lots of changes to make on that, but you can sort of copy paste things if you want with mouse and keyboard and Control C or so forth. Like I just use the standard Unix copy utility, say old file, new file, and now in my P4 stuff, I'm going to have this Shellac main created here. Of course, this says everything about lists and so forth and all that stuff. I'm going to get rid of that and call this the Shellac main. One quick tip on this. Most of what you need to include is in the shellac.h header, and we can look at that in just a minute. But making that change over here will include like all the standard I/O and standard a standard lib. That's what I was looking for, malloc and so forth on me here. So that's a good start. And another quick tip, the command line echoing feature is a -- echo here. That threw one student I worked with off. So making that change here will be good. And of course, we'll need to make a bunch of other changes because there's a bunch of mentions of lists and so forth in here, but we can work on that as we go through. I'm not going to bother too much here with this, printfing business over here, because eventually I'll jump over to the project and find, okay, where's that help function that Kaufman gave? So over here, that's in the printing help over here, so I just copy and paste that in, and we're good. So not going to bother too much with that. I will, however, want to modify some things with the list here. Like none of that stuff is particularly useful. Just make a note here of replace with shellac stuff. My wild one over here, I may as well look, the prompt is supposed to be shellac, so I'll plop that down here. And this part I'll need to eventually replace with a what is it? F-gets here for that stuff. Because that's going to be, I don't want to intermingle fscanf with fgets here. But a lot of the rest of this stuff then is like, okay, like there's an exit and there's some other things here. I may as well just jump down here and, comment out a lot of the rest of this stuff here. And this is starting to look, semi-sensible for that. In order to satisfy the make file that's provided, if we look at that thing, I'm pretty sure that we need to provide these other two files on here. So the shellac job.c and shellac control.c, those will be needed to compile the ultimate shellac application. So we may as well plop some stuff down for those. A quick way to do that, we can just make some empty files. Actually, I can't remember if GCC will accept empty files or not. But we may as well do one quick thing in terms of setup, which is for problem 2 and problem 3, there's an outline of what's to be the required functions that are in shellac job.c and shellac control.c. So we may as well just grab these and copy and paste them into appropriate files there. So this is an outline of the functions with some documentation strings about what those functions are supposed to do. So I'll find that here, shellac job.c. This defaulted to the testing file instead. So plop that down. Now I don't know for sure if GCC will like the fact that these are a bunch of prototypes rather than actual function bodies, but we can modify that in just a second. And I'll find shellac control.c, and over here, do as usual, we'll get the outline for this stuff in there, and then we'll just see if this compiles for us. Okay, so I'm not sure, but now I think there's probably some problems in main that I did because I was doing it in a hurry, but there's likely also, I don't know, let's just try the build and see. So in the wrong directory, so I need to find that P4 code here, and then I'll build. Let's see, shellac job needed by, oh shoot, did I do it in the wrong directory? P4 code. Yeah, I think I did. I put no? Is it up here? Okay. Confused. I expected that to do something else. Is there not a shellac job.c in here? Oh, yep. Must have spelled something wrong. Shellac job. Oh, I wrote it. It's shell, then shell. Okay, never mind. Dummy. Quick Emacs tips for folks. There's a nice Dured mode here. So I said here I can just rewrite this thing as though we're a text file, and that'll stick. So name your files better than me, I guess. So files renamed. Okay. So type problems in shellac job.c because I forgot to put the header in. We can fix that. So here's there, and I'll just plop down a pound include shellac.h, and I'm pretty sure I'm going to need that in control as well. So I'll plop that down here. Okay, back to the shell and build. Let's see. An undeclared variable in main, but hey, my other two built okay. So let's jump back over to main. That was here, and I just forgot this success business. So I'll declare it just because I'm sort of in a hurry here. And then unclosed paren. That's it can be slightly more problematic. Oh, that's because I forgot to close the while loop there. I think that might do it. Hey, there we go. Okay. And then if I write shellac, hey, there we go. So like print, and it doesn't do anything because main doesn't do anything. So I'm not sure I can even exit. Oh, it does honor exits because that's the first one I checked. Hey, there we go. Partly done there. So this puts me in a position then to run the tests. I'll do a make test prob 1. And it starts and exits, so I got that going for me. And maybe there's some other stuff with echoing here that I'm getting for free on that part. So at any rate, this is not a bad start. Certainly, I'll have to start adding some things, but the help will be easy to add in. And then start working through case analysis to say the 0th thing in here is it's one of the built-in commands. So it even down here start to get rid of, well, actually, no, I'm not going to get rid of this stuff. I'm just going to alter this one to say, well, I'll be interested in something. Are you the command help or something like that? Importantly here, this CMD business is no good. That's what's getting read in up here. And instead, I'd want to start using some of the techniques that are outlined in here with fgets. And there's discussion of that in the basic interactive loop down here, printing help, and then let's see, the input line and tokenization here. Making use of fgets, so I'd probably want to, grab stuff like this. The in file in this case will be standard in, so make use of that. The 64 is a bit short, so I'd strongly recommend to folks, if you look inside of the shellac header, which is here, there's some buff size like 1024 characters or max line 1024 characters. Declare yourself an array that's either max line long and use your fgets on that array instead. But I certainly am not going to do that for you right now because that starts to smack of like just giving out solutions, and this is a good start. All right, so things to keep in mind then. After you get problem 1 done and your interactive loop up running, you're going to shift gears to start working on attempting to build this underlying functionality to launch a single child process, single child job at a time. And as you scroll through and look at descriptions of this, the main feature that is used to abstract over the Unix process is this job T struct. It's a glorified sort of struct that has some information that essentially is like, here's the child process. Things that you'll need for this then are, you'll have to fill in a name for the job. This will be like the 0th thing like GCC or WC or seek or something like that, as well as then the entirety of its command line arguments, how many there are, and there's some additional information over here as you start to run it, like what does it do eventually? Does it return something or does it fail in some way? The details for this are somewhat more outlined in the header file. For instance, there's this condition number, and there's a mention of job cons over here. If we bop back over to the header, which was here, you'll see beneath this down here a bunch of job cons, and these are essentially just numbers to plop down to indicate certain features about, I just created this job, it was just initialized, or it's running right now, or it exited normally, or it failed for some reason over here that Shellac detected. Those are the essential values that will be plopped down for this condition. And they're distinguished from, this program returned 0 to indicate success, or this program returned 1 to indicate a failure of some type. So what condition you're in, running, well, if I don't expect this return value to be anything. What condition are you in, you exited, well, then I can expect you to be something. What condition are you in, you failed, this will probably be a -1. But manipulating this job T struct then is the first thrust of problem 2, where you'll build out the functions that are described, let's see, in this job shellacjob.c file, doing basic things like print out information about it, which is useful for both debugging and for the use of the testing framework. There are a bunch of unit tests that will examine, like, oh, do you create jobs, like, do they look as they're supposed to? And this will be like allocate memory for one, eventually start the job. And this will be where a process is forked off. And up to the point of starting it, this PID should be like a 0. However, the job names and stuff will contain things like GCC with a bunch of arguments and so forth. But at the point of starting it, this is when you say, okay, I'll fork off a child process. If I know I'm the child, then I will exec a GCC-O, myprog, etc. The parent process, Shellac, will then change the condition, like this is, I've got now a child process that's running, I know it's PID, and eventually I'll check on it and so forth. And Shellac then maintains this little array of such jobs where there's a max number supported, I think it's 256 in this case, but we won't reach nearly that in any practical settings here. But each element is just a pointer to some job that's running. In the second problem, you're only going to have one at a time, so it'll always be the 0th element of this array, and count will be 0 or 1, 0 or 1, etc. And there won't be much use for like the sort of background stuff. That's problem 3 stuff. But that's enough trouble. So you'll fill in some of the functionality that's mentioned in this the job functions that are over here. You'll see in the doc strings there's some functionality you don't need to do for problem 2. It's relegated to problem 3. So it may be worthwhile to think ahead a little bit, but you don't need to work too far ahead on that stuff. But all the functions in here need to be in place for problem 2 to be finished, and then to be compatible with problem 3. There's probably some ways you can sort of hack around it, etc. As well as then in Shellac control, there are a number of functions as well that each of these needs some functionality implemented for it. And there's less guidance here about problem 2 versus problem 3, but you'll probably be able to sort that out yourself on it. And these are functions that basically just manipulate one of these Shellac keys, which is an array. It's like we're adding a job in, removing one, you're updating everything in there, you're waiting on one of them, printing over them, etc. So hopefully that'll be reasonably self-explanatory, but if you need clarification, just ask, and we'll provide that. Okay, so after you get done with problem 2, you'll be able to start Shellac and run jobs, and then problem 3, which is the last part, and it's not exactly the most complicated, like you won't write a ton more code there, but it is conceptually somewhat more difficult in that you're going to add some detection of on a command line, is there an output redirect, is there an input redirect, are there combinations like I'm both output and input redirecting or redirecting inputs and launching something in the background. That's something that you'll need to check for as you create jobs and then populate certain fields in the struct with it. So there's spots here for output file and input file, and a little flag to indicate is this a background job or not. And then some separate modifications to other parts. For instance, as you start a job, over here there are notes on like IO redirection, like where is it that you actually do that IO redirection. It's usually in the starting, because after you fork, this is where you're going to do some dupe 2ing in the child process so that the output does not go to the screen. It instead goes to some output file that's created. And there are some specific options that are over there that you'll need to pass to open system calls. So as you round around to that, make sure to read some of this stuff and follow the directions accordingly to be compatible with all the tests and expectations. And all these I chose just because they're sort of standard for what most normal shells would use for both the options and the permissions for the files that are created over there. And the background jobs one then will have you messing around a little bit with, okay, I got to make sure that I'm adding jobs and removing of the right spots. I think it's worth noting that, let's see, I'm trying to think of where I can find an example of this. Is it, cheers? Oh no, there's a discussion of it. Where the flip is it? Okay, there's some discussion of like how the Shellac T thing. Yeah, okay, here. The Shellac control, like a file, it deals with this jobs array and a Shellac T. So for reference, here's my Shellac T. It's got an array of jobs and a count of how many jobs are in there. this array has a slightly weird feature in that it's non-contiguous necessarily. So it's highly probable that you have a bunch of jobs running, but the 0th job is null because it was run and completed. It's just these later ones at index 1 and index 2 and index 5. These are the ones that are in the background still running, so there are null gaps in here. And so you'll have to be cognizant of that and work through the jobs array a little bit differently as you're working with Shellac. And as you'd ask, hey, what background jobs have I got running here? Print that out from Shellac and say, there's nothing in the 0 slot, so I won't bother about printing out there. This is an LS and a GCC and a WC for the 5th. And this is more or less how Bash would work as well. I'm trying to think if I'd feel good about trying to quickly initialize that in Bash, and I'm not going to bother. But this is a required behavior, so keep that in mind as you're working with the jobs array, that it's actually null terminated, or sort of full of nulls in there and non-contiguous. And that can lead to certain sort of coding tactics then as you're working with it that may be a little unfamiliar. Okay, I've rambled for far too long on this, but hopefully you are able to extract some information there. I think I forgot to mention one other meaning for shellac that is somewhat colloquially is to have the crap beaten out of something. So like the Terps got shellacked on Saturday because they lost 47-0, and it's often used in sort of sporting context there. My hope is that implementing this program does not shellac you, but ask for support. This is due well after Thanksgiving, so you should have time leading into it as well as time after it to get assistance from course staff. The amount of code to write is not tremendously large. A lot of it is sort of boilerplate stuff, but getting it all fit together and seeing this is where those system calls actually come into play is what makes this an interesting and worthwhile endeavor. All right, happy hacking, and I'll see you again soon.